Now, what is ideal in ideal solution? That's a question, right? Now, we can always go back to like the gas phase thing. Gas phase thing in the sense, like what is ideal gas? Now, if you remember that ideal gas is something like we discussed all these real gas pictures, right? Like Andrew's curve, and there we just drew the isotopes, and we said that in a very low pressure region, this region, right? Every gas behaves ideally, right? So all real gases will behave ideally in the low pressure level. Okay, which means ideal gas will be something which behaves ideally. Ideally in the sense that it is obeys this equation, ideal gas law. Okay, at all pressure. If it had behaved ideally at all pressure, then it's an ideal gas. Okay. Now, similarly, we can also say that for ideal solution also. Okay. We can call an solution an ideal solution. Okay. If it behaves ideally at all pressure. Now, what does it mean? Okay. Now, solution means what? Solution means actually I have two things, right? Solvent and solute, right? Now, again, this solvent and solute is kind of like comparative, or it's your perspective in the sense that the amount which is in large excess, that is solute, so that is solvent, okay, and which is in small excess, that small extent dissolved in that solvent, okay, that we call as solute, okay. Now the thing is, for the time being, let's say we are assuming that this solute is involatile. In the sense that if I just keep it in a container, okay, only the solvent will be appearing in the vapor phase. Okay. Now, what do you mean by that? Suppose I have a sealed container, okay, and I have solvent, okay, and what will happen at equilibrium? It will develop some pressure which is equal to the vapor pressure, right? At some finite temperature. How do you measure it? You can actually connect like this, okay, a manometer kind of setup, okay, and you can actually see what is the difference in these levels, and from that you can calculate what is the vapor pressure, right? As simple as that. Now the question is, this is suppose for a solvent, which means actually I am talking about a pure solvent, okay, like it's not a solution, it's just a pure solvent, okay, and now, what we are going to compare is, I have the same solvent, but now I have a solute also. Okay, but if the solute is involatile, again the vapor pressure will be contributed only by the solvent. Okay, now the question is, what is the difference between these two vapor pressures? Okay. And usually you will see the vapor pressure here in the solution will be always less than the vapor pressure when the solvent exists as pure. Okay. Now there are different notations in different textbooks. Okay. So we'll just use this star notation for if the solvent is pure. Like P star will denote basically pure solvent's vapor pressure, something like that. Some textbooks actually use this zero notation, meaning say P0, but P0 I think we are already using for standard state pressure. Okay, so just make this distinction. Okay, now let us move on. Okay, and let us first try to understand how the vapor pressure should change as we basically increase the concentration of the solute. Suppose on this axis I am plotting pressure and this axis I am plotting the mole fraction of the solute. Okay. Now again, solvent means actually I have two components, right? Solution means I have two components, solvent and solute. Now we can actually use some 1-2 notation. One we can keep for solvent and two we can keep for solute. Okay. So in the solvent, I am keeping the notation 1. And for solute, I am keeping just the solution, the notation as 2. Okay. So x2 basically denotes the mole fraction of the solute. Okay. Now think about it. When the mole fraction, what should be the scale? Mole fraction can be maximum equal to 1. Okay. So it will just vary from 0 to 1. Okay, it's a fraction, right? Now when it is 0, what does it mean? It's a pure solvent, right? Now pure solvent means actually, so that pressure according to our notation will be something like P star, right? Okay. Now when it is 1, okay, so then which means actually it is 100% solid, right? But the solute is insoluble, right? If the solute is insoluble, then that time the pressure, if I have 100% solute only, it will be 0 because there is no vapor pressure, because it's not coming in the vapor press, right? So it's an involatile solid. So what will happen? I'll have basically some thing which will connect these 2 points, right? Now I'm saying if it behaves ideally, okay, so then it will strictly follow this line, which means the vapor pressure, okay, will be lowered. Okay, if I keep on adding the solute, okay, and if the mole fraction of the solute increases, okay, and reaches at a point where actually it is a pure solute, basically, then I'll have 0 vapor pressure, and in between if it varies linearly, okay, then I'll call this behavior of the total thing, which is the solvent, as an ideal solvent. Okay, sorry, of the solution as an ideal solution. Okay, so this is basically the behavior for the ideal solution. So ideal solution has 2 limits. One is pure solvent limit, one is pure solute limit, right? And in between basically it's the solution, but actually both are present. Clear? Okay. Now of course you will not like nothing will basically behave like this. Okay. You will see deviations. Like for example, you will see some deviation from here, like this. Okay. The real curve will be something like if I just draw it as a solid line, it will be something like say this. Now think about it. For a real curve, okay, what should happen? If I have very low concentration of the solute, okay, which means this region, right? So this region, what should happen? Like I have a low concentration of solute, right? So I have not only an ideal solution, I have an ideal dilute solution, right? Because dilute means what? Dilute always we say with respect to how much solute is there. Suppose I have a solution of sodium chloride in water, right? So if I have a little amount of sodium chloride, so the mole fraction is much close to 0, right? So that time the real curve will actually asymptotically approach, right, the ideal curve. Also, when sodium chloride, I have suppose pure sodium chloride in a container, okay, and it doesn't vaporize, okay, at room temperature, then also the vapor pressure should be 0. So this curve should also touch this curve, okay, when mole fraction of the solute is 1, okay, but in between the behavior we have no clue, okay. So we can only describe things when the mole fraction of the solute approaches close to 0, or in other words, when actually we are talking about a solution which is a dilute solution. Okay, clear? Now let us come back first to the ideal solution behavior. Okay. Now, so what can be, how I can actually write the equation for this? It is very easy. Let's say that it's just y equal to mx plus c. Okay. So it's a negative slope, and the slope is basically equal to -1. So we can just write it that the pressure, okay, equation will be something like we can write it as P star minus P. So that will be equal to, let's say, this one. I'm just following a particular notation here. Let's write it this way. So for this section, you can follow Castellan's Castellan's book. Everybody has probably. Okay, but the notations I'm using little bit for Matkins. Okay, because the P0 and P star there is a confusion. Okay. All right. So the pressure, what I just said, will be P star when actually x2 is equal to 0. right? So I can actually write it, and pressure is equal to 0 when x2 is equal to 1. So I can actually write it like this. Okay, just check it. When x2 is equal to 0, I have piston. Okay, and so basically the slope is minus piston. Okay, and the slope becomes intercept. That's why I am getting 0. Okay. Now we can just write it. What is 1 minus x2? If I have only solute and solvent in two component system, it is basically x1, right? So I could have written it as piston into x1 also. Okay, these are different ways of writing. Now look at it very carefully. What we wrote? Okay, so we wrote that the pressure. Which pressure is it? It's the vapor pressure in presence of the solid. Okay, is now P star is a constant. Why? Because P star corresponds to when the solvent is in pure form, right? That has to, whichever condition you measure, as long as you have constant temperature. Okay, then P star is constant, right? Now, which means actually P is proportional to x1. Okay, or the vapor pressure of a solvent, okay, in a solution is proportional to the mole fraction of the solvent. Okay, that is basically the meaning of that dotted line, which is a straight line. Okay, and that is the Raoult's law. Okay, however, as I have shown here, Raoult's law will be valid. This thing will be valid for real system only when, okay, this mole fraction x1 is close to 1 or x2 is close to 0. Okay, which means when the solution is dilute. Clear? So only in the dilute, very dilution limit, this will show the ideal behavior. Okay, so an ideal behavior means actually the pressure, maybe you can actually write it here. Okay, so this is basically vapor pressure of solvent, okay, in the solution. Okay, so that is basically proportional to the mole fraction of the solvent. Clear? Okay, so these are just notation. I mean, many people use like try to drop the x1 notation here. They just write x, okay, for solvent, and 2, 3, 4 for all the solids. Okay, we'll see what happens if you have like multiple solids. Okay, all right. Now, what will be the basically the thermodynamics of this system? Okay, and we can again start with any of the standard functions. But again, we are talking about, say, at constant temperature. Okay, and when the system reaches equilibrium, then the pressure is also constant. So constant pressure temperature means we will again look at the Gibbs free energy or Gibbs free energy per mole, which is the chemical potential. Okay, and when the system is in equilibrium, the chemical potential in the solution as well in the vapor should be same. Okay, of what? Chemical potential of what? Solvent. Okay, I cannot talk about solute because the solute is not in the vapor phase. Okay, because the assumption is that the solute is non-volatile. Okay, now so we just try to actually keep it very simple. Okay, like what we are going to say is that, okay, the mu, okay, in the two phases should be identical, right, when the equilibrium has been reached. So what I am saying is that the mu, okay, in the solution phase, okay, is equal to in the vapor phase. Okay, we can actually write it. Just a minute. So this mu actually means actually of solvent. Okay, don't get confused. This is for the solvent. Okay. Now the solvents, vapor, chemical potential in the solution and in the vapor are identical. Clear? Okay. All right. Now, what is like in the solution? Okay. So how I can actually write it? So I have to write in terms of vapor. Now you think that we have already developed the equation. What is that? Mu is equal to mu0 plus RTL and P, right? Now that we can apply for ideal gases. Okay, because if you remember how we wrote that equation, mu was basically G by N, right? And everything came from a fundamental equation. dg was minus sdt plus vdp, right? At constant temperature it was vdp term only, right? And then that v we replaced by ideal gas equation, and that gave us this equation, mu equal to mu 0 plus RTL, right? So if the vapor behaves ideally, right, then actually I can write it as mu is equal to mu 0 plus RTL, okay, only in that condition. So this is kind of an approximation. Okay. So it is something like mu 0 of the vapor, okay, plus RT ln P by P. Okay. But again, this is for the vapor. Okay. Now let us think about it. So what is P? Already we showed it, right? So if P is basically the pressure or the vapor pressure of the solvent, okay, in the solution, which is proportional to the mole fraction x1. So just replace it. Okay, we'll just replace this P by P star into x1. Here. Again, there are many like pressure terms here. That's why I'm just trying to asking you to pay attention here. Okay, so what I did is that I just said that at equilibrium. Okay, suppose at this condition. Okay, I have basically two things. 1 plus 2. Okay, I have solvent which is I'm denoting as 1 and solute which is denoting as 2. Okay, but here I have only 1, not 2, right? So what I'm saying here is that the chemical potential of 1 is same in the two phases. Okay, that's exactly what I wrote. Okay, in solution and in vapor it is same. The vapor equation now I am replacing, assuming the vapor behaves ideally. Okay. Now what is P? P is now the vapor pressure in the solution, right? Now vapor pressure in the solution, we already said that if it behaves ideally, okay, it will be equal to P star into x1, where P star is actually the vapor pressure when there is no solute. Okay, star means actually pure form. Okay, so let us just write it. So we can actually write it something like that. This is nothing but mu 0 vapor plus RT ln. We have this should be basically P star by P0. Okay, and then I'm just using ln AB is ln A plus ln B. Okay, so I'll have an extra term which is RT ln x x1 basically. Okay, clear? Okay, all right. Now let us think about it. Okay, this is for the solvent in a solution, right? So what will be the mu of the solvent if it is in a pure condition? It will be just mu star, isn't it? What I am trying to say here is that, okay, so everything is written for solvent first of all. Okay, so this is solution, this is in vapor. Clear? Okay. Now tell me, if x1 is equal to 1, what does it mean? That is in the pure form. Okay. So in that case, basically mu star solution, okay, is nothing but mu 0 vapor plus RT ln P star by P0, right? Plus RT ln x1, but that is 1. Okay, so this entire quantity is nothing but mu solution star. Clear? So I can always replace this thing. So mu solution in general, okay, that will be equal to mu star. Mu star means actually it's always pure solvent. Okay, I should not write it as solution. Okay, plus RT ln x1. Clear? Okay. So what I did is that I have basically written it as 3 terms. Okay. These two terms, now I am saying if x1 is equal to 1, okay, that term vanishes, but x1 equal to 1 means the mole fraction of the solvent is 1, which means I am talking about pure state. So that mu is nothing but a mu star. Okay, so this entire quantity is nothing but actually mu star. Okay, so I'm just using that notation. Okay, so I basically established a relation, okay, which is for the solvent in the solution. Okay, now some textbook actually write it as simply as this: mu is equal to mu star plus RT ln x. Okay, this is the equation for the solvent, okay, or component 1. What is mu? Mu is basically solvent's chemical potential in the solution when solute is present. What is mu star? Chemical potential of the pure solvent. Clear? Okay. And x is basically mole fraction. So now let's see what we did actually. We actually did everything in the solution thing, like in the condensed phase. We actually equated the condensed phase with the vapor phase. Vapor phase had two terms, right? So we just took out the mole fraction term, but still it is the vapor term. This vapor term is identical to the pure solvent term. Okay, so that is the trick we did. Okay, and these mu's are all in solution. Okay, got the point, right? So everything is now in the solution. Okay. Now the question is, okay, fine. So we wrote it as with respect to what? With respect to solvent. Okay. Can we write it with respect to, say, solute? Okay, that's a question. Now, if you remember that, so let me actually, for your convenience, okay, let me actually write this notation. I think that will be better. Let us just write it as 1. Okay, that will be better. Okay. Now, suppose I want an equation for mu2. What will happen? Okay. So, any solution means there is a solute also, right? But solute is very difficult to do. Why? Because I did not have any equilibrium to start with. There is no solute in the vapor phase, right? So I started with solvent. That was the only thing. Okay. But now I have to play a trick. What is the trick? The trick is that I have to somehow get an equation of mu2 and x2. That's what I want to establish right now. Now x2 is very easy. x2 is basically 1 minus x1. Okay. But the question is how mu2 and mu1 are connected. That's the question, right? Now, if you remember that we discussed an equation which is known as Gibbs-Duhem equation, right? So, what we did basically for multi-component system, okay, or say to be simple, two-component system, what we wrote it as minus SDT plus VDP, right? Plus we wrote it's a sum of mu I dni, right? That term. And then what we did, we basically said at constant temperature and pressure, it's only the mu I dni term. Then we integrated it and differentiated it. Okay, and then we found when you do a differentiation of, say, AB, you will get A dB plus B dA kind of thing. So the second term will be automatically equal to 0. Okay, so which was basically d mu I was 0. Sorry, mu into dni was 0. Okay, so we'll just use that. So just to remind you what we did, okay. At equilibrium, this was basically 0, right? Then we integrated it. We got mu I into ni. Again differentiated it, okay. And since this part is 0, we wrote basically ni dmu I. Sum of that was 0. Okay, that was the Gibbs-Duhem equation. Now, what is I here? I is basically 1 and 2 because it's two-component system. 1 is for solvent, 2 is for solid. Okay, so now it is very simple. What I have here is n1 dmu1 plus n2 dmu2 is equal to 0. So I'll directly get a relationship between mu2 and mu1. That's what I wanted to do. Okay, so let us just follow the same notation. Okay. So this is what? This is Gibbs-Duhem equation. Okay. Now I want actually basically a relation between mu2 and mu1. So I have to integrate this. Okay. So just do it. So d mu2 is nothing but what? I'm just taking it on the other side. Okay. I'll have n1 by n2 d mu1. Clear? Okay. Now I'll integrate. Now before I integrate, let us actually play a slightly different trick. Okay. So what is n1 by n2 at say constant pressure and temperature? Okay. Anybody? Okay. So this is basically ratio of the moles, right? Now think about it. If I just write it as say mu equal to mu0 plus RTLN that way, okay, in one for the one solution, what should I get? So like I have say mu1, okay. So what I'm saying here is that can I actually write, okay, the mu1 as say for example at constant temperature and pressure for the solvent, okay. What will be basically d mu1, this term, okay. Think about it. What is d mu1? We already wrote what is mu1. This thing. Okay. So d mu1 will be d of mu1 star, but mu1 star is a constant, that is 0. I'll have basically a RT by divided by x1 dx1. Clear? Okay. So let us just write it. Okay. So I can actually write it as minus n1 by n2 from this. Okay. And I'll have RT ln. Sorry, I'm taking the derivative of ln also. It will be dx1 by x1. Clear? Okay. Because see, what I want actually eventually, I actually do not want basically these n notations. Okay. The reason is, as you can see, right? It is basically what we have finally. I have RT dx1. Okay. RT by x just like it will be RT by x. Just ignore. Okay. Now what is n1 by n2? n1 is what? Moles, right? Now I can actually divide denominator and numerator by total number of moles. So the n1 by n2 is nothing but x1 by x2. Okay. So that we can have actually changed here directly. Okay, x1 and x2. Okay. Still I have a small little thing. What I want is that I want a mu to x2 kind of relation, but I have x1 here. Okay. But 1 and 2 is easy because I know x1 plus x2 is equal to 1. Okay. So if x1 plus x2 is equal to 1, dx1 is nothing but minus dx2. Clear? So I'll just replace this thing but by minus dx2, and instead of x1 I'll just write, I can write 1 minus x2. Okay, then I'm done already. Okay, so let us just write it. So again, what we are doing right now is going from a Solute equation for 1 to an equation of 2. Okay, and again I'll just repeat it once again. Okay, once we are done. Let us use this phrase. So what we can write finally here, so d mu 2 is nothing but dx1 is minus dx2. So this minus gets plus. Okay. So if I now integrate it, okay. So what I'll have basically, I'll have mu 2, okay, is equal to RT by x2. Again, t is constant. Okay. Yeah, I'm coming to that. Okay. So dx2 by x2 will be basically ln x2, right? Plus there will be a constant of integration. Okay. Now how do you determine the constant of integration? Again, that's a trick. Trick in the sense like I can always see, in this case, if I just see this kind of equation, okay, I'll just ask what will happen if x2 is equal to 1. If x2 is equal to 1, c is basically mu 2. But x2 is equal to 1 means what? pure solute. Okay, that is basically mu to star. Something like we just did. Okay, so this guy is nothing but mu to star. Okay, so ultimately what we get is mu2 is equal to mu2 star, okay, plus RT ln x2. Okay, now you see these two equations. Okay, exactly identical equations. Okay, only 1 and 2 got interchanged. But the idea is that we cannot actually approach it at the first place. Why? Because the solute was involatile. Okay, so what we did is that we just took the solvent to be volatile. Okay, established an equilibrium, got this equation. Okay, then I asked this question, can I actually get a relation of mu2 to x2? Okay, and there actually we used the Gibbs-Duhem equation. Alright, and then basically wrote all these d mu's, d mu1s, okay, instead of d mu2, and then just d mu1 you can get it from there. And also the second thing is this thing, okay, x1 and x2 will always add up to 1. Okay, but now the question is, what is the physical significance of this? Okay, now think about it. If x2 is basically, I said, equal to 1, okay, the mu2 is basically will be equal to mu2 star, okay, which means actually I'll basically approach, okay, the pure solute, okay. But now the question is, conceptually, can I now trace back to the origin of it and say something like it can also be derived as some pressure equation? Meaning, how we derived it, how we got this term. We got this term, remember, that from the pressure equation, because liquid was in equilibrium with the vapor, okay, and it was the vapor pressure, but the vapor is behaving ideal. Now, can we actually logically say the same thing here? Actually not. Okay. Now, the beauty here is that although it's not connected as a vapor, because we initially said that there is no vapor, okay, mathematically, x1 and x2 are kind of behaving ideally. Okay, like the way actually the chemical potential is changing. Okay, so we cannot actually draw anything like this for that two thing. Why? Because it is obvious, because it is involatile. Okay, there is no concept of P2 or P2 star. Okay, because it is involatile. However, it also kind of, okay, behaves in such a way that the chemical potential of the solute in the solution, okay, is less than the chemical potential of the pure solute by an amount which is RT ln x2. Why it is less? Because x2 is a fraction, okay, and ln x2 will be a negative number always. Similarly, this is also less. Okay, so to summarize, what we did is that we actually were interested in what is the chemical potential of a substance in a solution. Okay, what is it for solvent and what is it for the solute? Okay, now the trick we played is that when we are considering solvent, okay, the solvent exists in vapor and this solution, okay, and they are actually used all this mu equal to mu 0 RT ln P, okay, for the vapor phase. From there we basically calculated this equation, arrived at this, and using Gibbs-Duhem as well as for material balance for two component system, we arrived at this. Okay, so inherently the solute of the solvent, okay, it really doesn't matter which one is 1 and 2, as long as, okay, you are only looking at the solution. Of course, there is, you did not look at the vapor, okay, but you use the vapor equation very cleverly for the solvent, because the solute doesn't go into the vapor phase. Okay. However, the chemical potential or the nature of the chemical potential, the change, which is basically the decrease, is the same for 2. Okay. And then you could actually write that the mu2 or the chemical potential in the 2 is also has the same functional form as x2. Okay. Now that is basically connected to the other law, which is known as, there are two laws, Raoult's law and Henry's law, right? But then Henry's law say it's a slightly different concept. Okay, so what is Henry's law basically? If I actually instead of x2, okay, I could have actually plotted as a function of x1. See, the variable is x2 is nothing but 1 minus x1, right? And if I had plotted it as a function of x1, how it will look like? It will be the other way. Why? Because basically the axis is getting inverted, right? X1 is basically for the solvent, right? Now, what you get is basically the curve will look like something like this. Okay. So both are ideal solution, these dashed lines. But when actually the amount of the solute, okay, is going to be very, very less, okay, which means actually when we are approaching the dilute solution limit, then only these things will hold, either from the solvent's perspective or from the solute's perspective. Okay. Again, solute and solvent are your choice. Okay. But again, we arrived at it, okay, keeping in mind that one of them, either whatever it is the solute, okay, has to be volatile. Otherwise, we cannot arrive at this. If both are volatile, okay, the problem will be in the vapor thing, which you wrote very earlier, right? Something like we can actually write it for the solute also. Okay. So then the problem will be in the vapor phase. Okay. The vapor pressure will not be equal to the vapor pressure of the solvent, but it will be the partial pressure of the solvent, because the solute is also involved. Clear? And then we have to actually think about it. Like, I mean, it's a similar thing, but then actually we'll have many, like x2 will also come, because the partial, you have to write it as a partial pressure and the total pressure. Clear? Okay. So we'll see that thing. Okay.